to my old friends. If it talks, it's the second of my friends and collaborator too, Victor Buchstaber from Moscow. He shares so many places that it's very difficult to put two of these places he wrote. There are some others. About his hobbies, really, I don't know his hobbies. Maybe he's very skillful, not only scientist, but administrator, which is very rare combination. He's the editor of several journals, a member of different committees and so on. But he's very, very nice person. So I hope the talk will be.
Okay, thank you. My old friend, Bishop. So, okay, at first, of course, thank you very much for organizers, especially for Professor Kate Moffat and Professor Monastyrsky, my friend. And certainly, it's a great pleasure and honor to give talk here. Anytime when I give talk in this Isaac institution, I obtain so exciting feeling. And thanks for all, because it's a great pleasure. Okay, let me start. Okay, I hope it worked. No. Before worked.
When we left?
No. Maybe not immediately. Yes. This talk about our result with Elena Bunikova. We will discuss the dynamical system which arise in classical and modern problem of mathematics, mechanics, and biology. I show this system. And my main goal, not explain some additional application of this system, but show some new approach for this classical area, how arise new interrelation, interplay between this system. So it's my goal such. For such system, we introduce the notion of algebraical integrability and discuss a wide class of algebraically integrable system. Okay? Yes, we can go. At first, the main definition. We will consider linear space with coordinate C1, Cn. Sometimes useful using Cn when we discuss the meromorphic function, and Rn when we discuss the smooth function. And quadratic dynamical system, it is nothing else as such system on n-dimensional vector, where what this tensor is constant. Of course, we can consider the space of all quadratic dynamical system and obtain what such dimensional linear space of such tensors. And our activity, topological, dynamic, and so. Let me explain how related what these topics with the dynamical system is evident, with topology. Of course, this dynamical system related with differential geometry. We can see this. But for me, will be very important using very strong topological tools. It is a grading. It is exactly, I mentioned it, I consider not a quadratic dynamical system, but I consider the homogeneous. For me, T has grading 4, coordinates -4, and constant has the grading 0. In topology, very often we're using such additional features, and I show that it is useful. Okay.
Sorry, and ij is the same?
Sorry. Yes, 0.
So it's upper script, so it means this.
Of course, A, I, G, and K. No, it is a. Okay, you're right. Okay, not problem. Then, yes.
Sorry, what exactly do you mean the degree of T is 4?
Exactly.
Sorry. Degree T is 4, a degree Ci -4.
Why is the degree of T 4?
Yes, because if you're using this, you obtain immediately that what this system became is homogeneous. You see, In the left, you have degree -4, but in the right, you must obtain -4 too. But in calculation, it is a very useful. In topology, all times we're using this. Yes, yes, yes. Scaling, but scaling certainly useful. And one of the main step in my construction will using exactly
But
degree.
why not 1 and -1?
It related, let me repeat, in topology. In topology, manifold has the negative degree, and also it is you can change. You can consider T -4 and Xi +4, but relation must be same. Okay?
But why not +1 and -1, say?
No.
No?
I can give you, it is a very bad. If it is odd, it is not good. Even, you can ask me about 2 -2.
Yes.
But no. Okay.
You will explain why.
Yes. Okay. Next, let me show you at first the classical dynamical system. You can see the system. You see?
Why is it important that it's homogeneous?
You understood when I show you my method. It will be certainly. Before you trust me, it's useful. It's okay. We have such classical system, and I named this Euler top. Of course, in the classical Euler top, you can find some coefficient, but very soon we will using the group of symmetry, and I can consider the normalized case. So it is a normalized Euler top, and of course, you know that with this dynamical system has with such family of integrals with such condition. But immediately using this system, you can write down this system for any n more than 3. And not so simple to find all integrals for this system, but in my approach, we find the solution of this dynamical, not only this classical solution, but in for this system too. But for any n more 3, we can write out such generalization of Euler top. Okay?
Just to understand, you should replace J by I +1 on the second line formula.
Yes.
Because unclear, Xi I, Xi J.
No. Let me explain. No. You see, the first, in this approach, the first line extremely important. You see, after that, we're using cycling. 1 go to 2, 2, 3, 3, 4, and last n minus 1 to n is 1.
Can you tell the second summand in the Xi 1 prime?
No, yes.
3, 4.
Explain me. I give you very strong instruction. Using the first line and using the cyclic permutation. It's enough. It's enough.
Excuse me, does prime denote time differentiation?
Sorry.
Does prime denote time differentiation?
Yes.
Oh, yes.
Ah.
Oh, yes.
I don't
Prime. Sorry, okay, of course, yes. What?
Yeah, the Euler top
Yes.
form is dictated by a group of rotation.
Yes.
So what is the group in n space? It has nothing to do with rotations here.
It depends on, but very soon we understood that it is certainly what nice system. Euler top, it is some model. Very soon we met Euler top in very different situation. Because exactly I mentioned dynamical system in mathematics, mechanics, biology, and so. In any area arise the same system, which from different interpretation. Okay, so no, not immediately. Sorry. Yes. Sorry. Just a moment. We will soon. Yes. At first, so we discuss this. Let me continue. Okay. Let us consider the Darboux-Halfon system.
which is different from what you just showed.
Yes, Certainly, because I like introduce wide class of dynamical system which will be integrable in my sense. Of course it is different, of course, but this dynamical system appeared in the 1878 Darboux analysis of triple orthogonal surface. And now we know a lot generalization of this system, but very soon, you see, often find the solution of this system using the theory of modular form. Yes. After that, I should like introduce other generalized Darboux-Halphen system. It is a look exactly such, but T square, it is a such quadratic form, and Halphen find the solution for this system too using the theory of modular form.
What did it mean he found the solution? He could write it down on paper?
Yes, in paper he described Xc1, Xc2, Xc3 as function of T. Okay. Next. This and this. After that, let's go for the classical question to the more modern question. Let T1, T2, Tz be n cross n matrix valued meromorphic function in a complex variable z. Here exactly we consider the complex case. The NUM equations are a system of matrix differential equation in such form, you see? The same symmetry, 1, 2, 3, and after that you can bisect change. But here it is not vector, it is a matrix. It is a NUM equation system. Okay?
There's matrix multiplication on the right, isn't it, or what?
But what does it mean? Here it is a commuter of matrix. If you have two matrices, you can organize commuter. It is a classical commuter of the matrix. Okay?
Okay.
And T is complex.
Yes. You see, n cross n matrix valued meromorphic function in complex variables. Meromorphic function, all entries in our matrix, it is a complex. Okay? But Hitchin show that this NUM system has the beautiful Lax representation, you see? If we took A in such form, where zeta it is the spectral parameters, and M in such form, where you can construct A minus 1, AO, A1 immediately from our T. So you start from NUM system, doing with such change of coordinates.
I think T3 is missing.
Sorry?
T3 is not missing.
What missing?
T3.
T2?
There are only T1 and T2. There is no.
Oh,
A0 equal minus 2.
Oh, sorry.
Sorry. T in center. A0.
of course, TC, sorry. Of course it is. Of course. AO is minus 2ET3. Of course, thank you. So, thank you. For us, especially interesting case where n is 2. In this case, our Tm we can take in such form where Cm of z is some meromorphic function, but sigma m it is a Pauli matrices. You see, such. And after that, if you put all these entries, you go back from the LAM equation directly to the Euler-Top dynamical system. It is exactly why I remove the momentum coefficient, because it is useful. Okay. What's the next? It turns out it is a special case, more general construction. Because let me remind you very shortly what is mean a reduction of self-dual Young-Mills equation. We consider vector bundle over R4 with the fiber isomorphic as linear space to the gauge-Lie algebra for the gauge-Lie group G. Then self-dual Young-Mills equation we can write down in such form, where F, this, is the curvature from the connection A, and is a Hodge-star operator. And Ablovich-Kovarty-Halbert obtained it in 1998, the generalized Darboux-Halfon system, which I showed you before, exactly as reduction of self-dual Young-Mills equation, where G it is the algebra of vector fields of S2 or S3. Of course, what this paper was based on the paper of Takhtajan and Ablovitz, where they give exactly such explanation. What is the relation between NUM system and self-dual Young-Mills equation? Okay. And the reduction which I mentioned gives the quadratic dynamical system, okay, the such form, you see? It is in six-dimensional space, And T square, it is exactly norm of vector T. But if you look on the system, you can find immediately that system has such integrals, but after that you obtain immediately the generalized Darboux-Halfon system, which was introduced by many years ago. But I mentioned about the biology system. If you look in the textbook, in the scientific paper, in biology, ecology, and chemical kinetical equation, you can find such kind of dynamical system. You see, C prime it is a d over dt as before, but such form. But for NS3, it is a system was considered by Sofia Kovalevskaya. He considered and suggests some question, problem related with this. But he considered NS3, but in some paper to Mitak Lefler, he mentions that she will be happy to find the way to understand what is the structure of solution with such kind of equation for any n. But you can check by hand, it is simple. So n is 3, we have such space of integrals, it's two-dimensional space with such condition. For n is 4, this system has two independent quadratic integrals such kind. But if n is more 4, there are no quadratic integrals, but the approach which I should like to show you very soon give to us the solution of this system for any n. But classically, it is a well-known question what we can say about the structure of this dynamical system. Okay? Yes. I finished to introduction to what kind of dynamical system was the source of idea which I should like show you. And let's go to mathematics and describe and discuss some ideas which we made here. Okay? After that, we obtain the answer which I promised. At first, because we consider not a dynamical system, but quadratic dynamical system, we can using more strong action of group G, L, and C. So, if we go from coordinate Xi to coordinate eta by constant matrix B, we obtain such representation of this group on the space of all these tensors. It is explicitly, we can check by hand, it is exactly, you have, you remember 1 over 2n and n square n plus 1 linear space of such system, and we have the group linear transformation which send system with such tensor to system for such system. More. Let us consider the symmetric group with the, as the subgroup in the Gaussian C corresponding to the action symmetric group on C, standard permutation of coordinates. Immediately we can introduce such notion. Our system is called symmetric if any B from permutation matrix does not change this system itself. Let me introduce some notion which give to us the possibility to describe our method for integrating our system. At first, let me remind you the classical object, the ring of symmetric polynomials. Ring of symmetric polynomials. And of course, we consider open manifolds Mn. It is such vectors where all coordinate is different. It is a typical. And after that, we obtain free action of our group on this manifold. And projection of orbit space, it is exactly covering, induced by the universal algebraic map, where vector this go to the vector of elementary symmetric function. And we can go to the ring of symmetric polynomial, which is, of course, ring of polynomial, which is subring on the initial ring of polynomial of Xi1, Xn. But we can consider our dynamical system nothing else as a vector field.
What is symmetric polynomial?
Okay, symmetric polynomial. At first, let us consider polynomial of variable Xi1, Xn.
Yes.
After that, you can action of this polynomial by permutation of coordinates.
I see.
As I mentioned, it is a classical very
Yes. Permutation.
yes permutation. But what was important? We go from the space with coordinate Xi1, Xn to the new space with coordinate H1, Hn, where the basis H1, Hn, it is elementary symmetric function, nothing else. Okay, so just a moment. Yes. So I suggest to consider such linear differential operator, you see, and say our system is called symmetric if for any symmetric polynomial applying this operator give to us other symmetric polynomials. And important that definition 1 and definition 2 are equivalent. So our dynamical system is symmetric if and only if this differential operator send any symmetric polynomial to symmetric polynomial. It's all. But after that, we can prove by hand, it is not so heavy, that each symmetric quadratic dynamical system has such form. It is a full answer. You can see symmetric quadratic dynamical system has only 4 free parameters: alpha, beta, gamma, delta. It's all. But it's enough. For example, if we consider the case of Lotka-Volterra, we have 2 free parameters, not only 1 and minus 2, any. But in any case, follow the general fact, we obtain the symmetric system.
But it's no longer homogeneous.
Why? All homogeneous. All homogeneous.
Delta.
Okay?
Delta.
Delta is constant.
It's delta times.
So it's delta times.
Delta times. Delta times.
No,
You see, alpha parameters,
Space.
beta parameters, gamma parameters, and delta parameters. All parameters are constant, but constant for me degree 0. So it is certainly what I like. Okay? So the first example exactly this. We have 2 free parameters which give to us the symmetric system. Okay. More. If we choose the multiplicative basis, homogeneous multiplicative basis in the ring of symmetric polynomials, you see, with such condition, we can introduce such function over t. Consider AKT, it is the symmetric polynomial of variables xc1, xn, t. But after that, we can write down our dynamical system in the space of symmetric polynomial such kind. It is exactly first step where important degree, because you see, it is in our case it is a one-to-one transformation, but you see how look our system. A k plus 1 go to this right part in the first degree, not quadratic. We remove all degrees. You see, a k prime t must be with some constant coefficient. Of course, cn must be 0 because we have only n variables, but as a coefficient, it is only constant. And we can say symmetric system is generic if in the system which we introduce, the constant is not 0. The property of system being generic does not depend on choice of multiplicative basis. It's fact. So sometimes you are useful using Newton polynomial, sometimes you can using the elementary symmetric function other. But in the case of Newton polynomials, such classical system look extremely simple. But you see, and now look such, all times such where k from 1 to n minus 1, it only last has the polynomial form where 1 over n, this is the classical polynomial expressing n plus 1 Newton polynomial in the Newton polynomial number less than n plus 1. It is exactly method, it gives to us the possibility to integrate such kind of system. After that, I am going to introduce the main notion. And I consider this as the new notion. What is new notion? Algebraic integrability. What is mean algebraic integrability of symmetric dynamical system? Consider the universal, consider the universal equation. We have h1, hn, so we can write down such algebraic equation, introduce delta, it is a discriminant of this equation, and we know what is mean, the classical. It is image under universal algebraic map S of this configuration where we met vector with coinciding coordinate. Definition. System 1 is algebraically integrable. System 1 is algebraically integrable in some open set U by set of function h1, hn if this vector not indiscriminant for any t from our open set, and the set of roots to the equation 4 is a solution 1 of any t. So, because our system is, let me give some comments, because our system is symmetric, it's enough to consider not function, but elementary symmetric of this function. Because if we know the elementary symmetric function, we can consider this equation and solve this and obtain solution of our system. It is exactly the main idea which I should like to show. Problem. Find an ordinary differential equation of degree n for h and differential polynomials h2, hn in h such that in the neighborhood U the set of functions where h1 is our chosen ht, other it is a differential polynomial from h, algebraically integrated system 1. So it is a problem. But it turns out for each generic symmetric system 1 with the initial data, which in our manifold, there is a solution to the problem of algebraic comparability in the vicinity of initial data. CTO, it is the initial vector. So if you have generic symmetric system, you can construct directly the algebraic solution of this system. It is a fact which helped to us to obtain application.
Can you show again the definition of
Okay, please.
previous slide?
This.
Previous.
Okay, please.
Yes, because it's strange. So
What?
several notion of integrability, but here you add with respect to a set of functions. So,
Of course,
so
it's definition.
you have the system together with set of function h1 and
No.
But
No. System 1 is algebraically integrable in U by set of function. So if you have some system 1, you must find h1, hn, which give to you algebraic solution. No.
in initial system you
have not this.
you had no functions
Of course, let me repeat, Mitya.
Not just interval, but interval by a set of
by a set of functions. So
What is mean?
I was-
Sorry. What is mean? It is English. I can explain to Russian too.
But I
Because
remember there
let me
was
explain. It is a system 1 algebraically integrable if you for your system can find such function h1 hn which give to you by equation 4 the solution of your system. And I show very soon as the system which I give to you before, all in such form. I have such dynamical system. People don't consider what such approach because my problem to find h1 hn and show for this h1 hn solution of equation 4 is the solution of system. It's all.
I'm just asking because I remember the talk of Alena Bunkova. And
No, not forgot about.
she could not answer the question.
It's your problem. It's your problem. It is your problem. But my answer was such.
Okay.
I am her teacher. Maybe he don't understood something. But let me repeat again. It is a very concrete definition. You start from some general symmetric dynamical system. Only. We don't only such generic symmetric dynamical system. It is the initial data. After that, I show how we can construct by hand h1, hn, which give to us solution. It's our result. Okay? Let me explain how we do this. Consider the system. Consider the system 3. This, you remember this system? Consider the system 3 and take ak is hk, being the elementary symmetric function. So I like to construct my hk in the term of elementary symmetric function. Under the condition of the theorem, we know that ck is not 0. Hence, hg t, which, what? Sorry, just a moment. hgt, where g 2 till n, can be expressed as polynomials in h1, hg minus 1, and their derivatives from the G minus 1 equation of system 3, because it is exactly we obtain from algebraical theorem. Thus, the equation H1 prime is this, last, gives the homogeneous differential equation only for H1. So we obtain differential equation for H1 with constant coefficient. After that, we obtain the solution of integrability problem. So we construct differential equation, we find the solution, we reconstruct H1, and it's all. And more, we can describe explicitly how look the initial data. Thus, we have reduced the problem of integrability of symmetric quadratic dynamical system to the question of solving an ordinary differential equation of such form with constant coefficient. Arise the problem. Classify the nonlinear ordinary differential equation obtained from generic quadratic dynamical system. It is exactly problem which arises any times. If you have reduction for some problem to the differential equation, arises the question, what kind of differential equation we obtain? It turns out the answer here very nice, and after very soon we obtain what kind of differential equation we obtain here. But let's go back to action of whole general symmetric group, GLNC. The system wide is said to be quasi-symmetric with respect to matrix B if the system in the new coordinate is symmetric. A quasi-symmetric system is generic if the symmetric system in the new coordinate is generic. Corollary, for each generic quasi-symmetric system 1, there is a solution to the problem of algebraic integrability. And this, it is very serious, because you remember our result, that the space of symmetric dynamical system, it is a 4-dimensional. But if we're using the action of matrix B, it is a dimensional n square. Very important example, which related with the classical question. If you consider R3 or C3, the space of dynamical systems has dimensional 18. Only 4 is symmetric. But using the group GL3C, we can add 7. So, in the space of all quadratic dynamical system in dimensional 3, dimensional 18, we obtain integrability for 11-dimensional. And I show that a lot system which I described before exactly in this 11-dimensional space. Okay? Okay? Because, let me repeat, if it is not symmetric, we can try to find the B which send our system to the symmetric system.
So if you change the coordinates,
Yes, 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 yes. It is exactly how we can obtain, for example, with normalized Euler top, the classical top. Exactly using the diagonal matrix, which is momentum matrix in the classical approach, and so on.
Your original formula for the dimension 45 for n equals 3.
No, 18, because we have such
Is the dimension of
A,
3 by 3
G, K, but it is exactly A, K, G, I, because it's a quadratic.
Yes.
After that, it's exactly 18.
Yeah.
Yes, thank you. What's the next?
May I ask again about symmetry?
Okay.
What is the symmetry? If you do the permutation on the right-hand side,
Let me show you this and it will answer for your question. You see? First non-trivial case, it is of course the case of two-dimensional space. Exactly the first classical Lotka-Volterra system arises exactly in dimensional 2, where you have two spaces. Okay? You see?
no.
The formula 7 give to us the answer. How look symmetric, quadratic,
Yes.
dynamical system dimensional 2.
Yes. This is
You see, you have 3 parameters. But not all is generic. Fortunately, the condition very simple. If beta not alpha plus gamma, it's enough. So you have 3-dimensional space and remove the plane. Beta is alpha plus gamma. After that, you obtain all generic. What's the next? Using the matrix B, such form, we can transform this symmetric to the non-symmetric. 8, it is non-symmetric. But again, 3 parameters, it look simpler. After that, the normalizer of dynamical system of the form is diagonal. What does mean normalizer? Because y arises 7. In the group, you have dimensional 9, but 2-dimensional, which worked on the space of solution. But we should like obtain. So the space of symmetric has the symmetry 2. The symmetry exactly 2. And only additional 7 arises when this. After that, okay, we obtain the answer. It turns out the group of symmetry of symmetric system looks, sorry, just a moment, very soon. Yes, this group looks such. The group of such matrix transform symmetric system to symmetric system, and this such. Okay, next. Yes. Dmitry, it is answer exactly for your question. We start from generic symmetric 2-dimensional system and obtain such differential equation of second order. But if you find the solution of this equation, you can reconstruct H1 by this explicit form. So, problem only find the solution of this equation. And the initial data for this equation, in the generic case, we can rewrite so. So, you can consider any initial data, but not in this manifold. It's all. So, if you find the solution, we solve this system. Okay? But very interesting to consider the special cases, because in dimensional 2 we have 2 parameters, lambda 1, lambda 2. If lambda 1 is 0, we obtain explicit solution, which is the elliptic function. It is a Jacobi sign. If lambda 2 is 0, we obtain the hyperbolic tangent, and only when we go for this special manifold, we obtain the rational solution. Let me repeat. It is a 3 important special cases which show that our differential equations of second order have non-trivial solution. Next. If you go from system to differential equation, arise the back problem. For given differential equation, find a dynamical system, and here I have not so much time. Here we solve this problem. So if somebody give to us such differential equation, which solution we construct by hand dynamical system, which is has this our solution. So it is a explanation how it is not so evident, but step by step we solve this problem.
You can construct for any n.
Sorry,
For any n.
the problem. Or-
The n is determined
No, no,
by the
no.
degree of the differential equation.
Yes, n it is a dimension we evoke our dynamical system. Let us consider the important case, three-dimensional case. It is exactly we have a lot, thus Euler top, Darboux alpha, and so on. Here we have such look the general three-dimensional symmetric quadratic system. You see, now we have maximum number of parameters. It is a 4 parameters. Generic case, it's exactly not so heavy. We have 4 parameters, and we must consider as the singularity theory configuration space by removing such two traditional. You must remove 2 hyperplanes, but open set give to you general symmetric system. Okay. It turns out, if we go to the special matrix B, we obtain such canonical form, which we can describe all parameters explicitly. Okay. After that, arises interesting question: what it is a group of symmetry, symmetric dynamical system? Answer looks such. It turns out now it is not torus. It is a torus ABC with such cubical relations and such form. Okay. Therefore, the subgroup matrices obtained from this subgroup by conjugation bring the space of three-dimensional symmetric quadratic system into itself. So we describe explicitly how look the group of symmetric dynamical system. Okay. And after that, Dmitry, it's for you. Because consider the classical Darboux-Alphen system. You can check by hand, it is a symmetric and generic. But apply our approach, we go from this quadratic system for the algebraic system where H2 in degree 1, H3 in degree 1, and only last, it is not linear, but only 1. And here work exactly a condition of degree. So we start from this, using our approach, obtain such dynamical system in the space of symmetrical polynomials. Okay. And theorem, the Darboux-Alphen system is algebraically integrable by H1, H2, H3, which I give you explicitly. But H1, it is a solution the Chassis-3 equation. But any solution of Chassis-3 equation give to you full answer of integrability, because after that you reconstruct H2, you reconstruct H3, and you obtain all. And my question, what we must do after that? After that, I have not so much time. I have 5 minutes, maybe less.
5 minutes.
Let me explain. It was exactly in the 19th century where Lazare Fuchs and Poincaré put the problem. I have the special topics, but I have no time, so in my word. What's the problem of Fuchs and Poincaré? They asked, we have some ordinary differential equation. What does it mean to solve this? Naive people like to find the answer in the term elementary function, maybe elliptic function. But they mentioned no. If you have ordinary differential equation, you can describe the analytical property of this solution much better than in artificial formulas. Problem only one. What kind of differential equation is the initial? You cannot investigate any differential equation. You must introduce basic differential equation which give to you, follow the Fuchs and Poincaré, new function. After that, answer such. You have ordinary differential equation. Using analytical property of the equation, you must find the basic differential equation which give to you function. And your answer will be in this case. The first example was exactly this. It turns out the Chassis-3 equation looks such. It is exactly one of the basic differential equation. Now you can make in hydrodynamics and any physical problem arise such differential equation. Question, what we must do? Try to solve this or describe the property of this solution, it's all. And now we have the solution of Fuchs and Poincaré problem such, we must describe the analytical property of Chassis-3 equation, it's all. And now we have very nice paper where this done. After that, we can mention we show to you how we can solve the Darboux-Halfman system. What is the next step? General Darboux-Halfman system looks such. You see, additional term, parameter b, and this term. Follow our approach. We obtain this differential equation. You see, if c is 0, you go back to Chassis-3 equation. But in general case, it is a new differential equation where c is minus 4k square minus 36 is a Chassis-12 equation. It is other basic differential equation which give to us the new function. After that, let's go to generalized Darboux-Halfman system which arise in the problem of Young-Mills duality equation. In this case, we have such tau, and in this case, it turns out exactly why useful using not only matrix B. It turns out if we using matrix B such form, we can send this Darboux-Halfman system to the previous system and obtain solution in the term of Chassis-12 equation. And the general Darboux-Halfman system implies the system 3, but in such form, where we describe explicitly how look H1 this system. You see? It's all. Okay, maybe stop it, because after that we can describe the result about 4 dimensions or so. But I hope I introduce the method which give to obtain the answer. And let me repeat, the cornerstone for this method, first, it is a notion of generic symmetric dynamical system. And the second stone, it is a Fuchs Poincaré approach to the problem of integrating ordinary differential equation. Thank you.
Some questions? Oh, sorry. Okay. No.
Just would be very useful if you could give a reference where to read.
Oh, yes. Thank you.
This question is nature.
Oh.
Right.
Very soon you obtain this, but now it's enough to look in our big publication, Function Analysis and Application, and in archive this.
Thank you.
Okay.
Yeah, the Poincaré idea for solutions of an ordinary differential equation. You had a third order equation at one point.
Sorry?
Right?
Sorry, what?
If I thought of numerically integrating,
Yes, yes, yes,
I would have to start with 2 or 3 initial conditions.
yes.
Now, you talk about the Poincaré, you know, just the solution.
Yes.
It's really some huge class of solutions, isn't it?
No. Let me, you see, idea was such. The Poincaré asked, what is mean new function? And you, if you should like obtain this answer as a physicist,
Yeah.
you will be happy to obtain the single valued function. And after Fuchs arise the question, could you consider some differential equation? Can we answer the solution is single valued, is multi-valued? It turns out for this question we can give very strong answer. Now it is mentioned Penlevier test. You can using Penlevier test for your differential equation and obtain, if Penlevier test worked, your differential equation give to you single valued function. After that, it's fantastic, because when Penlevier start to using this test in the case differential equation of second order, he find only 50 differential equation as basic, because they show all other you can transform for this. But inside this 50, only 6 was new. And Penlevier mentioned, you see, it is not so heavy, it's not huge, because if you obtain the differential equation of second order, you can using elementary function, elliptic function, and only Penlevier 1, Penlevier 2, Penlevier 6, no more. What do Chazy? Chazy consider this problem for the differential equation of third order and find Chazy 3, Chazy 12, and so. So now it's the people worked. But I remember when I was a student in Moscow University, Vladimir Arnold many times mentioned it. I don't like the Cardano formula for the cubic equation, because it is a 18 valued formulas. But if I should like obtain the answer and I know the coefficient, using computer I can obtain immediately with exactness which I like here. Most important was to obtain the answer for your differential equation, the solution, it is single valued or not. Because it is single valued, you can use the computer to obtain the answer. And our happiness that we show that for many famous symmetric dynamical system, our differential equation exactly worked under Penlevier test.
Well, there's maybe just a coincidence, but you mentioned that the Lotka-Volterra equations, starting from n equal 4,
Yes.
n equal 5, you cannot solve.
No. Answer such. If you look in textbook, you can find Lotka-Volterra type system where n more than 5 have not quadratic integrals.
Good. Does it have some connection with the fact that Galois theory gives you also, starting from 5th order, you cannot solve, and the polynomials?
Good question, but for me important that from our approach, it is nothing. If I obtain the differential equation of 5th order, I can solve this. I don't need it, this extraction. But you asked other question, it's good question, why?
Yeah.
Why? It's okay. But it's not for me because it's interesting question. Thank you.
But it's not a coincidence.
I don't know.
No.
I don't know.
And is it? Sorry. What is the? If you consider a set of fixed points
Okay.
The right-hand side is 0. What the symmetry of the system, what condition does that impose on that set of fixed points? For example, does it give a condition on the dimension of that set?
Not only, most important that we can, what you see, if you have differential equation, you can ask about the critical point of this. What is mean of Penlevet test? The critical, you have not critical singularities which depend of initial data. It is exactly why arise single valued function. But of course, if you ask me about the pole, a solution also, but I understood this.
My question is much simpler.
Okay.
I'm talking about the original dynamical system.
Yes.
Not the differential equation.
Understood, understood.
So you can have, for example, if the right-hand side is just psi1, psi2, psi3, then the dimension of the critical points, set of critical points, is n minus 1.
Yes, in general case, yes.
But in other cases, it can be, I suppose, 0 or 1, or, the dimension of the set of critical points, to me, seems to be rather important for the structure of the solutions.
I agree.
So, does the symmetry impose any condition on that set of critical points?
Yes, certainly. Because what's idea? You have Cn with coordinate Cn. You go to the covering to the after symmetry, and you obtain the new space. After that, your critical points you can describe in much simple system, which I show you in the term H. After that, the critical points in the pre-image was more simple. It is the idea was such, when you walked in the system, if you walk in the initial coordinate X1, Xn, it is this, all coordinate have the same degree, -4. In new coordinates, only one coordinates first have degree -4, other have degree higher. It is exactly why our system became so simple, because in n-dimensional space, all variables have the same degree. It's not so simple to describe the structure. We go to this and obtain new space where variables is grading, coordinate is grading, and only one coordinate has minimal degree. After that, it gives to us the possibility to describe the property of dynamical systems and so on. It is exactly why symmetric much better, because coordinates became different degree, and you obtain the additional parameter for expansion your series. Okay.
So no question, so I small question.
Well, no,
Can I
Vadim хочет.
One more question. You've been using the coordinate language for the most of the talk, but apparently it can all be done in completely coordinate way.
Oh, yes.
Coordinate-free way.
Yes, of course. More, you know, the such Arnold convolution algebra. It is a language of Lie algebras without coordinate. Exactly, Arnold convolution algebra. But in my talk in the Arnold 75, I give explanation in such form.
This is maybe I ask a simple question because case price of this. So there are some relations between your approach and classification of integrable series by Penlevet using this moving.
Yes.
So is it some direct relations? But is it possible to find some direct relations, the integrability in Penlevet case and with these equations?
Yes. Thank you.
Regular system.
Yes. It is exactly when, if I show you the case, no, in dimensional 3, it's classical. Okay, we finished. In dimensional 4, arise new differential equation of fourth order with Penlevet property. Because our method, what we do, we consider the well-known dynamical system and produce differential equation which is new, which is this area. It's work not only this direction, other direction.
Okay. So, sorry, so now we wait by the reception, and so it's necessary to finish our section. So thank you once more, Vitya.
Thank you. Thank you.